Markov chains moved by matrix, Poisson processes by continuous clock. The simplest model of all just adds up coin flips. Heads, step right. Tails, step left. That's a random walk. And despite the simplicity, it hides some of the most surprising results in probability. Let x1, x2, and so on be independent, identically distributed steps, +1 or -1, with equal probability. The random walk is Sn, the running sum. S0 equals 0. Sn equals x1 plus ... plus xn. It's a Markov chain in its own right. The next position depends only on the current one, plus a fresh coin flip, but it's also a sum of i.i.d. variables, which puts the central limit theorem back in play. Watch a sample path, a jagged line wandering up and down, one step at a time, with no memory of which way it came from. Two numbers describe it completely. The expectation, E of Sn, is 0. The walk has no drift. Up and down cancel on average. The variance, var of Sn, is n. Because the steps are independent, variance is just add. So the typical size of Sn grows like root n, not like n. By the central limit theorem, Sn over root n converges in distribution to a standard normal. The same bell curve however you got here. Here's the surprise. In one dimension, the walk returns to 0, with probability 1. However far it wanders, it always comes back, eventually. The same is true in 2 dimensions, recurrent, but by a thinner margin. In 3 dimensions or higher, it changes. The walk is transient, with a genuine positive probability of never returning home. That's Polya's theorem. A drunkard finds his way home in 1 or 2 dimensions, but a lost bird in 3 dimensions may fly off forever. Zoom out far enough, and something remarkable happens. Rescale time by n, and space by root n, and the jagged walk starts looking smooth. As n grows, S at floor of nt, divided by root n, converges to a continuous random path, W of t, Donsker's invariance principle. That limiting object has a name, Brownian motion. The random walk was the discrete scaffolding all along. A random walk. Sums of i.i.d. steps mean 0, variance growing like n, recurrent in 1 and 2 dimensions, but transient beyond, a Markov chain, and a sum of random variables at once. It's the bridge between everything discrete we've built and the continuous time processes ahead. Rescale it, and the jagged path becomes smooth. Next, Brownian motion itself, the continuous time limit, and the process underneath stock prices, physical diffusion, and the rest of continuous stochastic calculus.